who dare to speak in this forum.
Okay, welcome. Yeah, Alessandro gave a really good introduction into the problem of the space debris, so fortunately I wanted to speak that much about it. Just about the concept I have conceived for actually taking out some of the space debris population, which are more specifically the cosmos stream and second stages. For this study in particular, I'm considering just one stage in particular, but of course this can change, and this will change, of course, because the mission is a multi-target mission. So let me first start with just describing the outline. I'm going to start with really just one slide about the space debris environment, and then I'm going to jump to the reference mission. So defining basically the goal of the mission and its definition, which actually drew the concept. They're actually the basis of defining the concept. Afterwards, I'm going to just guide you through the brainstorming ideas, main trade-off, and the selected concept itself. And then I'm going to talk about the coordinated control architecture concept, which is basically what do I need to control the system like that I can see, and again just to conclude. So let me start with the space debris because maybe not everybody is acquainted with it, although Alessandro gave a really good introduction. So basically until 1957, we have had more than basically 4,900 launches, which put into the orbit 6,600 satellites, of which half of them is still there. So for a grand total of material which is written here, and 40% of them are illegal. So basically, and the future predictions we saw previously are the trend is going up. So we need to do something about it in order to just reach this situation here. So let me talk first about the goal of this mission. The goal is basically to remove multiple objects, not just one, of uncooperative cosmos stream upper stages using robotics. So I'm working in a robotics institute. So and to control the orbiting to limit future sources of space debris. With this in mind, I consider a mission scenario, which basically takes into consideration the reference target vehicle, which is the one defined in the US Space Track catalog with this ID. And it has this orbit here. You can see it, and it also considers this mission scenario, this Chaser spacecraft, which is a robotic spacecraft, of around 9 tons in my case, which is really heavy. Considering higher propulsion modules, not solid propulsion modules for the orbiting, and the mission consists in the orbiting several targets in sequence, basically. We control the orbiting with a single burn of around 70 seconds, an average thrust of 7 kilonewtons. So basically, this imparts around 0.5 Gs to the target, which is a rocket matrix. And the perigee of re-entry is below 60 kilometers, obtained via this delta V, which is basically obtained via igniting the orbital. So let me talk now to talk you through what I've done to come up with the concept that I will show you in a few minutes. So at first I have considered I have brainstormed some ideas along with some colleagues. Basically consider a bunch of studies here, a bunch of already existing experiments. Like for example, the most interesting to me were these two, which basically are developed by a company in Bremen, Festo, and they actually uses the fin array effect to grasp basically objects that have irregular surfaces. So basically with just one gripper you can grasp whatever you need. This, although it doesn't seem like this one, this is just lighter version used for like an octopus rover. Other concepts that I've taken into consideration are the microspines that are developed by MIT in JPL, and some other concepts that were considered in DFK, which are basically like using octopus arms, so basically multiple manipulators, multiple joints, which can fold around the rocket body itself. After I've done this, basically these brainstorming ideas, and after talking with some experts in DFKI, basically I come up with 3 possible solutions for my capturing concept. which are basically tentacles, so which is this concept here. The semi-rigid clamp, which includes something like this, and the robotic arm, which is basically the, let's say, the standard method we use to capture that we have already ready. So if you count the, let's say, the green areas, the clamp and the robotic arm are basically equal. But anyways, the robotic arm wins just because it can cope with targets that are tumbling like an order of 10 degrees per second, while the clamp needs a really, let's say, stable target. You need to compensate for the rotational rate by using your GNC. So with this in mind, I have come up with this concept basically, which uses the modules, the propulsion module and the avionics module of the ATV. This is why for some is actually the ATV. The two robotic arms, one for the capture, are used in sequence. So first I capture the target, and second, and then I stabilize it and rigidize the configuration by basically retracting and rigidizing the arm itself. And afterwards, I extract the orbiting kit, put on site, and place it into the model. So basically, in my concept, I'm using one arm at a time, which simplifies the control problem, and it also minimizes the dynamic coupling that are acting on the base because of the moving of the robotic arms. So what is here really important is to that the whole dimension of the spacecraft were driven by the orbiting kits, which I consider not solid propulsion, but high propulsion modules because of the regenerability of the solid propulsion module and their flexibility. And this is why, for example, this whole thing is so basically long because I needed to fit them inside. And what are the characteristics? So you can see basically the dimensions are those that I can basically fit inside the Ariane 5 as a single passenger. The mass properties I derived basically starting from the payload and using SMUDs, so basically space mission analysis and design books percentages, which is really rough, but for this first estimation, I think it's more than enough. So to come with math, it's around 9 tons. And yeah, the robotic arm is 7 meters long because I need to basically reach the most distant the orbiting kit. And the rest, you can see this is the power consumption based also on ATV's power consumption, which is the base of this spacecraft. So, although I have defined this as a best concept for this kind of mission, this with the mission definition I outlined before, there are some challenges I need to overcome in order to make the full usage of the concept itself. So it basically boils down to the development of a control architecture, which is basically it needs to predict the 3D position, so in space, of the capturing point. The system also needs to perform a workspace analysis and optimize the reachability, which means I need to take into consideration not just how to reach the target, but also will I collide with it, what is the best timing. Then, of course, to generate out of this the feasible trajectories, limit the contact forces in order not to push away the target itself, and limit the transmission once I grasp it to my base because I can't go with big angular momenta, which can be transmitted from the rotating rocket body to my spacecraft. In order to overcome this, another concept basically based on the previous one introduces a clamp, which overcomes this by basically synchronizing the relative motion with your target. So basically have zero relative motion and rotation, and you just clamp it. And the clamping mechanism is based on a prototype that have been done by some engineers in the FBI. It's really rudimental, but this is a finger of prototype of a finger of for a robot. So they have a more advanced version, but it's very simple just to show you. And it's cool because it can wrap around whatever you put it. So basically do something like this. And the good thing is that it can fold. So reducing the overall volume, which is something I would like to have here because I wouldn't fit inside the payload. And considering all the other methods which were in the brainstorming, Their own cool methods, their own clamping mechanisms are really proven, but they are all either heavy or occupy lots of space. So this is another alternative to the principal concept I have considered, but this needs a really good GNC, so to compensate for the rotational motion. So let me just introduce you the basically the coordinated control architecture in order to overcome the challenges I have just presented. It basically boils down in, onto basically making training of the robot to perform a certain action, in this case capture, and then so offline basically I have the target motion simulation and prediction, and then offline the motion planner, which gives basically to the spacecraft, which is here. So this is on ground, this is on the spacecraft, gives the initial guess, which then performs it in coordination with GNC architecture. And this is important, and this is something that's missing in the literature, because there's just DLR that is doing it, because every other, most of the research that I've found basically solve this online, considering all the assumptions. But this, I think, is something natural that is generally done once you, for example, want to capture on the ISS, you want to capture Soyuz or whatever space you want to capture. Basically, you first train the astronaut to do something so that he knows how to do it. Then afterwards, based on this experience, he performed. So this is the paradigm is here. And basically, the methodology is to perform the offline computation using machine learning, basically using two approaches, the black box approach and the parameterization. So parameterization is standard approach. Basically, I know what parameters I want to optimize. I just parameterize those outputs, so it is done by an operator, and then I propagate them through a learning algorithm to obtain the optimum. Or I can use a black box approach, which is really something that is really interesting, because it can come up, so basically we want the algorithm to come up with the best output to optimize, and then optimize it. But of course, if the search space is really big, this way we basically can come up with no solution. So this is something that needs to be taken into account. So to reduce the search space in order to basically come up with a solution here. But here, for example, I have found, for example, I just showed you in the brainstorming ideas, some configurations of how to capture a rocket body, basically where the algorithm comes up with this basically configuration, and somebody wouldn't come up with it, or it would be difficult for an operator to come up with that configuration. And the evaluation approach I would like to use basically is to implement everything in a software simulation tool that we have at FKI, which is Mars. And then, of course, compare with some results in the literature based on some case studies, and afterwards perform a Harman loop simulation system that we have in the FKI, and then mount a manipulator, of course, to test it. And the advantages, I just told you, basically the advantages are to cope with tumbling targets, as opposed to basically the clamp, to the motions of the spacecraft and manipulator are constrained because we are reducing search space. The dynamic coupling, which generally happens once you move the manipulator, which reduces the workspace of the manipulator itself, is basically limited because we are controlling the optimal configuration. And of course, the feasibility of the trajectory is guaranteed because we are taking into account the collision avoidance and the limits of the arm. The disadvantages are that basically it boils down that we need really good computational power. This is why this kind of approach can't be done on the spacecraft. So basically, we have the offline, on-ground computation, which then gets uploaded as initial guess. So, before concluding, I just want to talk a little bit, so just introduce you what are the equations, because we need some dynamic equations in order to basically optimize, in order to predict where target will be. So in this case, target dynamics. We have basically two dynamic equations, which is the first one, the Euler equation for the rigid body rotation, and the second one is the post-capture phase, where on the right-hand side we have forces introduced by the manipulator on forces and torques introduced to the centroid of the target spacecraft itself. Regarding the chaser dynamics, This is the generic dynamic equation for a spacecraft, where here we can see this is the matrix of inertia of the whole spacecraft, which doesn't include just the terms of the spacecraft individually, of the spacecraft and of the manipulator. There are some terms inside which are basically the coupled terms, which is something which complicates the motion planning of the space rover, because in space it's not really simple as in ground, because you try to grasp something here, but your body moves because there is no friction and you end up here. This is something that you need to take into consideration here and here, which are the Coriolis and centrifugal forces, which basically complicate the calculation of your position. So, just to conclude, the motivation is, as Dr. Rassano said, that we need to limit the sources in the future, we hope so, the future of space debris, because we are going, the population is going up, so we need to take something down. Cosmos 3M seem like the ones that are most suitable among all the others. The mass and geometrical properties are there for the Cosmos 3M, because I developed a CAD model based on some data, but the attitude is not known. So this is something that we need to take into consideration once we develop a concept for grasping. So this is why I'm considering basically what I presented is the concept for the capture that can cope with this. Actually, it should cope with this. And I presented 3 models of the space system. So basically, I have developed the CAD models, which will be used, translated directly into the Mars software that we have in the API. So in order to have basically ready simulation models, which will be plugged in basically to the dynamical equation that I just showed you. And then the concept for coordinated control, which should solve the problem. The future work, of course, consists of trying to develop a detailed model of 3D models of the spacecraft itself, integration side with software environment, and then, of course, it's development of a control architecture and testing. So, hvala na pažnji, or yeah, thank you for your attention.
Maybe I missed something or misunderstood. You mentioned that your facility will be able to catch tumbling bodies.
Yes.
What features, or maybe what algorithm will allow you to solve this problem?
So what algorithms I would be using?
Because when I look on these arms, I can imagine how they can capture an object in a principal axis rotation.
Yes.
But if we have a tumbling,
yes, what I'm actually expecting is something flat, basically flat spin of the rocket body, so not like this, but basically like this.
it's exactly
yes,
principal
yes,
axis rotation.
yes.
But you mentioned that you will be able to capture.
Yes, there is a limit, of course, and I asked some researchers, because we don't know what the real attitude. So I need to start building from the really simple rotation, and then trying to build around all the axes. In theory, if the model of the target itself is good enough, and including some perturbations, so not just because I'm here in the equation, not considering, yeah, there is a force here, of course. You can take it, this is just really what the dynamics, you can include here the force, so the external forces.
Okay.
If you include them, the system should be able to predict where it will be, and then thus basically optimize the trajectory in order to grasp it in advance.
Okay.
It should be, but yeah. We'll do our best. Yes, I know. Yeah, it's also, for example, here, if you take into consideration, they had the Japanese, so the JAXA performed some first simulations, and then performed an experiment with the ATS-7 satellite, which had a mountain automation. And generally, in space, you can consider, because these maneuvers happen in order of minutes. So you should be able to exclude all the perturbative forces which are in orbit, but it wasn't the case. They figured out that basically the gradient torque was large enough, and it needs to be taken into account here. So it's something that we need to take into consideration to counteract. And of course, the motion can be chaotical if we don't include, but we'll try to build up from the simple model, like this one, without including forces, and then building up as much as we can.
Does it need to download the calculation?
Yeah, of course, this is just for the study itself. But for the spacecraft itself, once first we don't have constraints of time, because once we are I don't know, around 100 meters, we can stay there with really relative control of the spacecraft there for days. And the thing is that you need for this motion just to download once. Then you have the solution, because you can propagate in time. Yeah. We hope, generally it shouldn't be, but of course everything here needs to be backed up by the data measurements from ground. There are some measurements done by CNES, but they didn't analyze the data yet. So I think there are some students working there on this attitude.
Okay, let's thank to Mark for one more time.